Welcome back to Differential Equations. In this video, I want to introduce you to some numerical tools for solving systems of differential equations. So, if I jump my head out of the way, I want to first remind you that we have studied some tools that we could use to solve a first-order initial value problem, something in the form y prime equals f of y and t, coupled with y of t naught equals y naught. And we saw that we could use Euler's method for this. We saw that there was the more powerful Runge-Kutta method, and they were very effective, or reasonably effective. And now, if you're thinking about a system of differential equations and a system of initial value problem, now we're looking at something that we have x prime equals f of x and y and t, and y prime equals g of x and y and t. And the initial conditions, x of t naught equals x naught, y of t naught equals y naught. And if you're looking at that and thinking it looks incredibly similar to that tool that we already were able to solve, well, you're entirely correct. We can use that same approach. We can say that t1 equals t naught plus delta t. We can say that x1 equals x naught plus f of x naught, y naught, and t naught times delta t, and we can say that y1 equals y naught plus f, it would be g in this case, of x naught, y naught, and t naught times delta t. And we can use the same Euler's method for solving a system that we could for solving a single differential equation. But as we saw for solving a single differential equation, trying to do this by hand is a complete pain. So it would be much better if we could get computer software to do it for us. And we can. In fact, the exact same tool that we used for solving the single initial value problem can be used to solve your system initial value problem. So we still have NumPy, we still have SciPy integrate, we still have pyplot. We have our system, so we need, instead of just an f, we need an f of x, y, and t. We need a g of x, y, and t. You can see here I have it set up. F is equal to y, so that's x prime equals y prime equals minus x. We have our initial conditions. At time t equals 0, I have here that x equals 1 and y equals 0. Same thing we've had before. We put in our value for the max value of t that we're trying to solve for. We put in our delta t, and then the rest of the code runs very similarly. And if you look at it, you will see that this line is directly from the previous, the single differential equation version. This line looks quite similar, but it's a little bit messier. And then I have this new thing u, which I've put the comment there. We want to write our system in vector form, and if we have it in that form, it is able to understand what's going on without any issue whatsoever. And then I've modified the graph, so instead of graphing y as a function of time, I'm plotting in phase space x and y. And of course, I chose the system of differential equations that produces a perfect circle. The radius of the circle is determined based on the initial condition. So if we have a particular x of t, if we have a particular x prime and y prime, then we are able to jump in here no problem. But also, as we've seen recently, solving a linear system as a linear system is usually not the most powerful tool. All right, so this is a particular differential equation that happens to have a name. It's called the van der Pol equation, and it is a second order ordinary differential equation initial value problem. We are given the second derivative of x minus 1 minus x squared times the derivative of x plus x is equal to 0. And then some initial conditions. How about x of 0 equals 1 and x prime of 0 also equals 1. All right, so it's a second order initial value problem. This is really the power behind phase space that we talked about for second order equations. If we let y equal dx dt, then y prime would be the second derivative. And we can take this equation and rearrange it. So we have y prime minus 1 minus x squared dx dt is now y plus x equals 0, which means that y prime is minus x plus 1 minus x squared y. And of course, just taking our definition of y and rewriting it, we have that x prime equals y. And there we now have a system of two differential equations. Our initial condition, the first one, x of 0 is equal to 1. The second one, x prime is just y, so this is y of 0 equals 1. And that system of two first-order differential equations gives us our format that we can put into the numerical solver. So let's jump back over here to the numerical solver. Let's see, our f, remember, and it gives us this in the notebook. dx dt is the function f. So dx dt, in our case, is y. We don't have to change anything there. G, that's our dy dt, y prime, which is a little bit messy. It starts with that minus x that's already there, but we also need the 1 minus x squared. And remember, double asterisks gives us squared, not a caret. That's a little bit messy. It's a little bit hard to remember. I really suggest using an internet search every time you're trying to put math notation into programming, because the formatting is not quite what you'd expect, and it's usually easy to find results on the internet rather than trying to memorize everything. All right, but let's go ahead and fit in our initial conditions. T naught was 0. But x of 0 is 1 and y of 0 is 1. I don't really have any max time, so I'll just leave that at 8. It's a number that's in there for the sake of being in there. And everything else should be set up and ready to go. So let's go to runtime. I have not run this yet, so I can't hit restart and run all. I just have to hit the run all at the top of the list and hope that everything works. All right, so there we have our solution. X and y when t is equal to 8. If that was something that was interesting to us, we have our result. Again, remember, x is the function itself, y is the value of x prime. So if this is a kinematics problem, we're probably looking at something based on Newton's law. We have the position and the velocity. We can also look at the phase space And while it doesn't give us a direction, we do know the initial condition. X of 0 is 1, y of 0 is 1. So let's see, we have 1, 1, which is here. That is our initial point. We did this awkward looking spiral thing. We went down, we came back up. And I guess we are spiraling outward, or maybe we are spiraling upward. I'm kind of curious to see how that goes. So let's change a little bit about our setup. We said to go until t equals 8, and that gave us something that looks really interesting, but I'd like to see a little bit more. So maybe a bigger number like 20 there will give us a little bit more detail. Let's hit runtime. Let's go to restart session and run all. Yes, we want to lose all of our information because, well, if we deleted something, bad things could happen. And now we've got this, and that gives us something a little bit more clear. We start with this point inside and we spiral out. And then we spiral back around, and when we get back up here, we practically are on top of where we were before. And it looks like we wrap around that a couple of times. So that's kind of interesting, and that's a very fascinating result. We start somewhere unstable, and then we make our way to a stable orbiting structure in phase space. Does that actually mean an orbit? No, certainly not, but it's a repetitive structure. There is something periodic about what's happening once we settle into the rhythm that the equation is modeling and trying to get us to be in. The physics behind where this equation comes from, what it's actually telling us, will be on the scope of this course as always. We're just interested in what's happening. So that leaves us with one for you to try. Let's look at something probably a little bit easier than the one that I just went through. I'll give you a system as a system. Let's look at x prime equals 2x minus 1.2xy. Y prime equals minus y plus 1.2xy. X of 0 equals 1.75, and y of 0 equals 1.0. Right, just to make sure that you are comfortable using the notebook file, but plug in this initial value problem, and it doesn't really matter what your end value of t is. I'm really more interested in seeing the phase space and making sure that you're getting this set up correctly in the first place. But I'll wrap up here, take a few minutes to see what you can do with that, and I'll see you in the next video.